Alright guys, today we're diving into one of the ultra coolest topics in astrophysics. Ultra metal poor stars. See what I did there? No? Okay. Well, I mean, it's in the name. They're ultra cool. These ancient stars are some of the oldest objects in the universe, and being the oldest objects, they hold the secrets to how everything around us came to be. So what are they, and why should we care? Let's break it down. No dancing. No?
Oh, brother, this guy stinks!
That wasn't funny either?
Nope.
Okay, fine. Anyway, first and foremost, let's visit our good old friend, the periodic table of elements, and clear up a common misconception. When we say metal poor, we're not talking about iron, gold, or whatever it's in your jewelry box. First of all, we realize that mostly everything in the universe is made up of hydrogen. Almost everything else is made up of helium. And these things down here, these things are what we call, well, supernova poop, I guess. It's not really the technical term, but whatever. What we really care about are the metals, which is what's in between the helium and the supernova. Okay, well, the rest of them, I guess. We also need to realize that almost none of the universe is made up of these so-called metals. Most stars have a little bit of these metals mixed in, but ultra-metal poor stars, they're almost completely made out of hydrogen and helium, elements that were formed right after the Big Bang. That makes them unique cosmic relics. So how do we actually measure how metal poor a star is? This is where the concept of metallicity comes in. Metallicity refers to the proportion of elements heavier than hydrogen and helium in a star. We usually use iron because it's easy to detect using spectroscopy, and it's a good indicator of overall metallicity. We write metallicity as Fe/H, where Fe/H is a ratio of iron to hydrogen. Metallicities are measured with the sun as a baseline. And keep in mind, metallicity is a logarithmic scale. Ultra-metal poor stars are at a metallicity of -4. Now bear with me as I go down the list, because physicists apparently are not that creative when it comes to naming things. A metallicity of -1, we have metal poor stars. At metallicity of -2, very metal poor stars. And -3, extremely metal poor stars. We finally get to ultra metal poor stars, and at the end we have hyper metal poor stars and mega metal poor stars. On the other side, we see metal-rich stars and etc. It's not really something we're concerned with right now. Keep in mind that ultra-metal poor stars have 10 to the -4th times the iron of the sun because it's on a log scale. So the sun pretty much has 10,000 more iron content than the baseline for what a star needs to be considered an ultra-metal poor star. Now, how do we identify these stars? We essentially use a process that is pretty similar to fingerprinting a star. Now, what would be on that thumbprint? What we do is called spectroscopy. By taking a telescope and observing a star, the light emitting from the telescope bounces off the star and returns back to our eyes. But this star is made up of elements that absorb certain wavelengths of light depending on what element it is. So when we split starlight into a spectrum and look at it, we see these absorption lines. And using these absorption lines, which can be shown as dark bands on a starlight's spectrum, we can figure out which elements are present and in what amounts. So, by finding stars with very low amounts of elements other than hydrogen and helium, we can detect how much metallicity a star has and deem it ultra-metal poor, or maybe just very metal poor. Now, why are they so important? Well, think of these as cosmic fossils. If you're a normal paleontologist, you're digging in the ground to find skeletons and fossils to maybe learn about how the Earth evolved and how these animals came to be. In our case, though, we look up at the sky at these very archaic stars. By studying them, we can learn what the universe was like right after the Big Bang. Think of them as time capsules that help us understand the conditions that led to the formation of galaxies, and even the elements that make up life. Let's look at this timeline. These ultra-metal poor stars were formed at about around 0.2 billion years, which is a long time, but in the scale of the universe, it's a pretty short time. Now, for a quick detour. When a star dies, it sometimes blows up in a gaseous explosion we call it a supernova. This supernova creates and shoots out metals, acting as sort of a furnace for these heavier elements. Now, at 0.2 billion years, because the universe was so young, there was a low number of supernovae, which means ultra-metal poor stars were created in an environment with low, heavy metals, which is why they have a low metallicity. Working backwards, if we find a star that has low metallicity, we can say that it's a really old star because it got created before tons of supernovae released metals into the cosmos. This makes these stars pretty much like fossils, but in space. We see now that ultra-metal poor stars tell us about the environment that they were born in. And in turn, learning about the environment that we're formed in can inform us about galaxy evolution, dark matter, and maybe we can even solve some of the most pressing questions in cosmology. Thanks for watching the video, and in the comments let me know what other...
Wait. All of you! Daddy, chill.
Let me know what other cosmic questions do you want answered. And keep looking up. See you next time, guys. Don't forget to like and subscribe. It's free, and you can change your mind at any point in time, and it really helps me out as well.